So far, we have seen that compact stars come in three major families: the white dwarfs, the neutron stars, and the black holes. And which star would form a neutron star and which star would form a black hole depends very much on the upper mass limit of the neutron stars. Now, we have also mentioned that the upper mass limit of neutron stars at the moment is somewhat uncertain, because the equation of state, that is the relation between pressure and density of neutron stars, is not fully certain as yet. So, in this module, we will take a look at some of the intricacies of the equation of state of neutron stars, try to understand what is understood, what is not, and where the uncertainty arises from, and what we can do to address it. To start with, let us recall the basic features of the neutron star equation of state. We know that in a typical neutron star, the matter is largely degenerate, which means the Fermi energy of all components, be it protons, neutrons or electrons, is much larger than the thermal energy of these particles. So, therefore, the role of temperature in the equation of state is insignificant. So, we can ignore temperature for now. We also know matter is in beta equilibrium, which means the chemical potential of neutrons is a sum of the chemical potential of the protons and electrons, and in some cases you would also have muons. So, the chemical potential will also include the muons. The proton fraction is a function of density. As the density rises from relatively low density, the proton fraction goes through a minimum and then it rises again as at high density, saturating at a value at about 1/8 or about 12% as density goes to infinity. Rough overall value over the entire neutron star is a proton fraction of about 10%. Now, as one goes from low density to high density in the neutron star interior, the nuclei get progressively neutron rich. That means, the ratio of mass number to atomic number keeps increasing as one goes to higher and higher densities. At some point, the A by Z becomes so large that it becomes difficult for the nuclei to hold any more neutrons within the nucleus, and at this point free neutrons begin to appear as an admixture with neutron rich nuclei which are already present. So, this is called a neutron drip. As one moves to higher and higher densities, the fraction of neutrons in the free phase, the fraction of dripped neutrons, keeps increasing. When one reaches nuclear density, which is about 2.4 times 10 to the power of 11 grams per cubic centimeter, the nuclei then cease to exist and dissolve altogether into free neutron, proton, electron matter. The lower density part of this equation of state is reasonably well determined. However, at the very highest densities is where the uncertainty lies. The equation of state at very high density regions has several uncertainties. So, in the interior of neutron stars, this is what we have. We have the surface where the material is like iron, the density of a few grams per cubic centimeter. But as we go into the interior, the density rises very, very rapidly. Up to about 4.3 times 10 to the power of 11 grams per cubic centimeter, the baryons are still fully contained within the nucleus. Above this density, neutron drip occurs and free neutrons begin to appear. So, you then have a mixture of free neutrons and nuclei. all nuclei dissolve at 2.4 times 10 to the power of 14 grams per cubic centimeter, which is the nuclear density. At this point, one has a mixture of neutron, proton, electron plasma. Material below this density is called the crust, and material above this density is called the core. At about 10 to the power of 15 grams per cubic centimeter or more, the nature of matter is quite unknown. The interior of the neutron star, where neutrons and protons are present, the neutrons interact via strong interaction, and so do the protons, and the interaction which is attractive between these Fermi particles causes them to form a paired bosonic state, which is a superfluid state. For neutrons, it forms a superfluid, and the protons form a superconductor, and the pairing comes from the attractive strong interaction. So, if we look at the structure of a neutron star, for example, here it is a computed structure of a 1.4 solar mass neutron star in a certain equation of state. So, what is shown in the diagram here, it is radius in the horizontal axis and density in the vertical axis, and one can see that the density rises above the nuclear density. That is the point at which all nuclei dissolve and the core begins. Starting from the surface, within about a kilometer, the crust is contained, and the entire region of almost 10 kilometers is the core. So, you have this inner core region, which is composed of just free neutrons, protons and electrons, which covers almost the entire star, and on top of it there is a crust which is roughly about 1 kilometer thick. Now, if you plot this in logarithmic scale, then one can expand the density region in the crust a little bit better, and one can see that there is the outer part, which is shown here in slightly reddish tinge. That is the region where all the baryons are in nuclei, and it is at this point, as you go to higher densities, free neutrons begin to appear. So, in this yellowish shaded region, you have a mixture of both nuclei and free neutrons. So, this outer part of the crust is called the outer crust, and the part of the crust where both free neutrons and nuclei coexist is called the inner crust. Now, the solid crust actually does not take much time to form. In a few minutes after the birth of the neutron star, the surface temperature already falls below the freezing temperature of the crust, and the solid crust forms very quickly after the neutron star birth. For a 1.4 times the mass of the sun contained in the full neutron star, the mass contained in the crust is only about 1/100th of the mass of the sun. So, the crust is a small part of the neutron star, both in radius, which is about a kilometer thick, and in mass it is roughly about 1% of the total neutron star. This shows how the proton fraction changes. So, starting from a relatively small value, it rises, and near nuclear density it goes through a minimum here, and then it rises again, and at the highest densities it reaches about 10-12% at the center. So, this is for 1.4 solar mass neutron star, this is the central density. This diagram shows the various components of the neutron star that I was talking about. This blue shaded region here is the crust. The core begins with this pink shaded region, and at the very center you have the highest densities, and the nature of the matter there is somewhat unknown, and that is why a question mark has been put there. So, you have the crust where you have nuclei. Initially you have nuclei which are spaced with a certain distance, and as you go to higher and higher densities, the nuclei not only become more and more neutron rich, they also become deformed, and they begin to take different types of shapes. They become columnar, and then they become sheet like and spaghetti like. So, the nuclei themselves are quite deformed near the base of the crust, and finally, the nuclei dissolve altogether, and you have just pure neutron, proton, electron matter with no nuclei in the core. What is also mentioned here is that the neutrons form a superfluid in this region. Wherever the free neutrons are present, both in the core and in the inner crust, free neutrons are present, and you have a neutron superfluid which is present there. And in the core, where also free protons are present, the protons form a superconductor. Now, coming to the question of why we have this uncertainty in the neutron star equation of state. So, this diagram is an illustration of what we can probe based on our terrestrial experiments. We have nuclear matter which covers a certain range of baryon chemical potential. The baryon chemical potential rises with density. So, a certain range of baryon chemical potentials are covered by the nuclei that we can measure and test in the laboratory. Then at lower chemical potentials and higher temperatures, we have experiments which one can do based on colliders, accelerators like heavy ion colliders and so on. So, when you use heavy ion collider, you can probe short distances, but because it involves a collision, you also raise the temperature of the material quite a lot. So, between this and high density hot matter, where you have quark gluon plasma, is what is the regime that is probed by different accelerator experiments. Unfortunately, neutron stars, the density and temperature regime of neutron stars are not covered by any of these experiments. So, neutron stars sit in this corner where it is very high density and very low temperature, and this kind of material is impossible to produce in the laboratory. So, that is why there is no direct experimental probe of how the nuclear forces behave in this region. Why can't we address this theoretically? After all, this is just a strong interaction, and from theory of strong interaction one should be able to predict what the behavior of nuclear forces should be in this regime. People of course have attempted this, but there are problems in the computational domain, because strong interaction by its very nature is very strong, and typically these calculations are done by summing a series, and these series are not convergent. So, one is not able to get clear cut answer by simply resorting to computation as of now. So, between what we encounter in terrestrial matter and neutron star matter, the main differences are the following. The terrestrial matter that we see around us is low density matter. The density is much less than the nuclear density, and the terrestrial matter is nearly symmetric. For any material that we see around us, the number of neutrons and number of protons in the nuclei are roughly similar. The neutron star matter, on the other hand, is matter at very high density, density at larger than nuclear density, and also it is extremely asymmetric. Number of neutrons is much larger than the number of protons. So, based on our terrestrial experience, based on our laboratory experience, if you want to extrapolate our law of force to the neutron star matter regime, any interaction that depends on high power of density or high power of asymmetry would make it difficult to predict the behavior of neutron star matter, because a small error in the extrapolation will cause a large error in the prediction because of this very high density and very high asymmetry. So, what do we know about neutron stars? At least what we can conclude reasonably well is that at densities below nuclear density, the equation of state is pretty well formulated. So, there is not much uncertainty or dispute at that point. Now, if you look at the neutron total energy in MeV as a function of the density, which is in the horizontal axis, then as you approach nuclear density and go above, then one can see that the neutron total energy rises rapidly. Now, as it rises, as it begins to rise, the value will begin to cross the rest mass of various other particles that can exist. So, various other hyperons and mesons can begin to appear spontaneously when the available energy bath is high enough. So, at higher densities, additional species may appear, and these include hyperons, heavy mesons, quark matter, condensates, and so on. Furthermore, even when discussing the forces between nuclei, we cannot restrict ourselves to just two body forces between two nuclei and so on. Now, the material is so dense, many body interactions play a critical role, and computing these many body interactions still remain a major source of uncertainty. So, these are a few reasons why the equation of state has still remained uncertain. So, the additional species that can appear at these high densities include hyperons, which are heavy baryons like lambda, sigma, delta, chi, and so on. Mesons, including pions, kaons, so that is both with and without strangeness. And once mesons appear at these high densities, they are likely to form condensates. Then quarks. Phase transition to deconfined quarks may occur with hybrid matter in between. And at sufficiently high density, a mixture of up-down strange quark matter may become the ground state of matter, which is below that of nuclear matter. So, if one is able to first make a transition to such a high density, then one may be able to access a ground state, which will then draw all matter around it to that ground state. So, if such a thing does happen, then the entire star may convert to this state, and such a thing would be called a quark star, and because strange matter is also present, the same thing is also called strange stars. These quark stars or strange stars are in fact self bound configurations. You actually do not need gravity to put it together. The interaction between the quarks themselves can bind the star. Now, all these effects which are listed here, appearance of additional species, appearance of quarks, forces between quarks and so on, all of these have the effect in the direction of softening the equation of state, which means the pressure at a given density becomes lower relative to that of nuclear matter if these things were not present. Softening the equation of state will bring down the upper mass limit. So, that is the consequent effect. At high densities inside the neutron star, a phase transition may occur to deconfined quark state. The phase transition is shown here in this diagram. In blue, we show the energy per baryon versus 1 over the baryon number density of a nuclear state, and in red the same quantity for a deconfined quark state. The common tangent between these two curves is the phase transition point. The slope of this curve is the pressure, and the intercept here is the chemical potential. So, at that value of pressure and chemical potential, which defines the common tangent between these two curves, is the phase transition that will occur, going from a certain density, which is characteristic of the nuclear state here, to a much higher density, which is characteristic of the quark state. So, this phase transition can occur deep in the interior of the star, where this condition becomes satisfied, and in the quark state, a mix of up, down and strange quarks may provide the most bound lowest energy state of matter, and the stars made of such matter would be called strange stars or quark stars. The quark matter equation of state is possible to represent in a relatively simple terms, which is through MIT bag model, where it is simply 3 times pressure is rho c squared minus 4 times the bag constant. And these stars held by this kind of equation of state will be more compact than neutron stars of the same mass, because obviously the number density has changed from a smaller value to a much larger value when you go to the quark state. Now, these quarks can also form something called a color favor locked state, which is a paired state. This is the densest state of 3 favor quark matter. So, here you have Cooper pairs of specific color flavor combinations, for example, a up and red quark and down and green quark and so on. So, red, green, blue are the 3 color states of any quark, and these are the flavor states up, down, then strange, charm, bottom, top and so on. So, these are the flavor families, and these colors are the 3 quantum chromodynamics color states. So, any quark can appear in any of these 3 color states. So, a combination of specific combinations of flavors and colors gives this color flavor locked state, which is a superfluid and is an electromagnetic insulator. So, this kind of state would be the densest possible and most stable and most favorable quark state if such densities are obtained at the centers of neutron stars. So, this will appear at fairly high density. So, if the central density of neutron stars reaches the requirement for this, then the quarks will more favorably appear in the color flavor locked state. So, there are all these possibilities which exist, and at the moment one is not really certain as to what really obtains at the centers of neutron stars. So, one is looking for experimental or observational constraints on the equation of state, and that is where both laboratory studies and the astrophysical studies of neutron stars become very important. The laboratory constraints on equation of state include measurements of nuclear binding energies, neutron skin thickness, dipole polarizability of nuclei, as well as giant dipole resonances, all of which can be measured in nuclear physics laboratories. Astrophysical constraints include the masses and radii of neutron stars. Of course, the equation of state determines the hydrostatic equilibrium and the relation between masses and radii, as we have already seen, as well as spins of neutron stars, oscillations of neutron stars, tidal deformabilities of neutron stars. All of these quantities, if they are measured, they provide constraints on the pressure density relation in the neutron star interior and hence on the equation of state. In addition, there are other general constraints that the equation of state must obey. For example, causality, that is the sound speed in the material should not exceed the speed of light. So, when you construct an equation of state by extrapolation from laboratory knowledge, this constraint must be kept in mind. The equation of state of matter should be such that the matter itself is thermodynamically stable, which means energy density will be positive definite and it should be monotonically increasing function of pressure. So, when equations of state are constructed from theories or by extrapolation from experimental data, one must keep in mind all the existing constraints coming from the laboratory measurements, astrophysical measurements, as well as these general constraints. Here, what is shown on the left hand side diagram are pressure density relations in multiple different equations of state, which people have predicted based on various types of extrapolations. And in this shaded colored regions are indicated the regions of pressure density relations which are allowed by the laboratory as well as astrophysical constraints. So, once this region is identified, only those equations of state which have their pressure density relation lying within these shaded regions should be taken as representative of possible nuclear matter and possible matter inside neutron stars. Once you have this pressure density relation, one can use the Tolman-Oppenheimer-Volkoff equation and then construct the structure of the neutron stars for non-rotating neutron stars. This if the neutron star is rotating, of course, as we already mentioned in the case of white dwarfs, TOV equation, which is meant for a spherically symmetric system, is not applicable. One has to use somewhat different formalism, but for most cases we will encounter neutron stars which are not rotating that fast. So, therefore, TOV equation is still a pretty good approximation. So, using that, from these equations of state, one can predict the mass radius relation. So, for each line which corresponds to one equation of state over here, there is a line here in this diagram which gives you the mass radius relation. So, therefore, if by observations of neutron stars, one can establish which mass radius relation neutron stars actually follow. We would have then placed a constraint on the equation of state and perhaps chosen one of these possible values, one of these possible relations which are enlisted over here. So, that is how the astrophysical study of neutron stars is a powerful method of constraining the equation of state of neutron stars, and thereby learning about how strong interaction in matter behaves at very close ranges. So, the range of these allowed equations of state translate to a range in the mass radius relationship, and that is shown by this red shaded area in this right hand diagram. Now, we come to the other attributes of neutron stars, they being the rotation and the magnetic field. Neutron stars are known to spin very fast. The fastest observed spin of neutron stars is 716 hertz, and the range of observed spins lie in the period range of about 1.4 millisecond to about 1000 seconds. Neutron stars also harbor very strong magnetic fields. The strongest known magnetic fields are about 10 to the power of 15 Gauss, and the range that one has observed so far lies between 10 to the power of 8 Gauss to 10 to the power of 15 Gauss, with the majority of neutron stars lying around about 10 to the power of 12 Gauss. So, these are extremely strong fields indeed. The magnetic field of neutron stars affect most of the properties of neutron stars, including the spin. If you take a strong magnet and rotate it, then an electromagnetic torque arises which feeds back onto the spin. So, left free to rotate, the electromagnetic torque will spin it down. So, the neutron star with a strong magnetic field, isolated neutron star with strong magnetic field which is rotating, will spin down because of this electromagnetic torque. On the other hand, if there is matter that is coming from somewhere else and falling onto the neutron star, and that matter may carry some angular momentum and transfer that angular momentum to the neutron star via the magnetic field and spin the neutron star up. So, depending on the situation, whether the neutron star is isolated or neutron star is accreting matter from some nearby object, the electromagnetic torques can cause the neutron star to be spun up or spun down. So, this is important in the life history of a neutron star very much. What we have shown here is a compendium of measurements of the spin period on the horizontal axis and the magnetic field in the vertical axis, the inferred magnetic field of neutron stars of various kinds, many of which are radio pulsars, which is largely located here. This set of yellow points show the bulk of the isolated pulsars. Many of the pulsars are in binary systems, which are sitting down here between this point and the lower down here. So, one thing to notice is this objects in binary systems tend to have somewhat lower magnetic field. For some reason, the fields in these objects have either been altered or been affected some way during this evolution. The large bulk of the neutron stars, as one can see in this diagram, lie in around 10 to the power of 12 Gauss, with the peak of the spin period distribution lying around a second. On the other hand, the fastest known neutron stars are over here, where the spin periods are close to a millisecond. You can also see the strongest field neutron stars over here. The spin periods are of the order of 10 seconds or so, magnetic fields going even above 10 to the power of 15 Gauss, which is extremely strong magnetic field. And the slowest neutron stars known are somewhere here, where the spin goes to about 1000 seconds, and all these neutron stars with slow spin which we see happen to be in binary systems. So, this set of neutron stars are strong field neutron stars, which are currently accreting material from a binary companion, and it is the interaction of this matter flow with the magnetic field of the neutron star that is causing them to be spun down to long periods. On the other hand, if the magnetic field of these neutron stars happen to be very small, then the interaction between the accreting matter and the magnetic field causes the neutron stars to be spun up to very short periods. So, many of these are products of such spinning up process in binary systems, and this line here corresponds to the maximal spin up that can occur in binary systems of this kind. So, as we said, neutron stars are seen to rotate very fast. So, for fast rotating neutron stars, the equilibrium solution has to be obtained in a manner which is different from just solving the TOV equations, and people have carried out this kind of computation and analysis. Typically, for a given equation of state, let us say I take one equation of state here, depending on the angular velocity, the mass radius relation will depend on the distribution of angular momentum through the star. Now, here what is plotted is the mass on the horizontal axis and spin frequency, angular frequency omega on the vertical axis, and as you change the central density of the neutron star for different values of angular velocity, you can produce neutron stars of the same mass, or for a given mass of the neutron star, you can have different values of central density supported at different rotation periods, and these curves envelope that region. So, for each equation of state, now you have these two extremes between the blue line and the red line. The blue line is where the configuration reaches maximum mass and goes through radial instability, and the red line is where the configuration reaches maximum radius, and once you reach this radius, the matter is shed from the equator due to centrifugal forces, and the configurations, rotating configurations of neutron star will lie between these two lines. Now, can the observed values of rotation of neutron star tell us anything about which equation of state is more suited to describe the neutron stars? So, as we see it, this is the largest inferred angular velocity of a neutron star. This is not just this 716 hertz that I talked about, but there is indirect evidence of somewhat faster spins in some other neutron stars. So, even taking the very fastest value that we could possibly infer, we can see that it is still not a discriminatory number for whether it is a stiff equation of state or a soft equation of state. So, at the moment we still do not have neutron stars which are really spinning very close to their breakup period for the spin to act as a discriminator between the different possibilities of equations of state. But we will see other discriminators which we do have in some of the modules to come. Now, coming to the interior, we see that you have fast rotation and strong magnetic field, but we already mentioned the material in the interior, the neutrons form a superfluid and protons form a superconductor, whereas the electrons are just in the normal phase. So, these three phases in fact coexist in the interior of the neutron star. These condensates like the superfluid, superconductor form a single macroscopic large quantum state to which one can ascribe a wave function of the form psi 0 e to the power minus I theta, where psi 0 is an amplitude and theta is a phase. And it is well known that in a quantum phase like this, a superfluid cannot carry rotation. On the other hand, the neutron star is rotating. The only way the superfluid can carry rotation is by creating singularities within it, which are called vortices, and each vortex carrying a certain quantum of vorticity. So, to rotate superfluid must make vortices. A superconductor does not need to make a vortex to participate in rotation. Instead, it needs to make a small magnetic field which goes into this extra term describing generalized pair momentum, and that takes care of rotation. But the superfluid neutrons must create vortices inside to rotate. However, this region also has magnetic field. The rotating neutron superfluid is permeated by an array of vortices, each vortex carrying a vorticity quantum of h by 2 m n, and there are about 2 times 10 to the power of 16 such vortices for a neutron star spinning at a period of 1 second. On the other hand, superconductor, which the protons make, cannot in general carry a magnetic field. Magnetic field should either be expelled or should be carried in quantized fluxoids, and it is the latter which is believed to happen in the proton superconductor which is in the interior. So, the proton superconductor carries the magnetic field threading the interior in fluxoids, each fluxoid carrying a quantum of flux which is h c by 2 e, and there are about 10 to the power of 31 such fluxoids for a magnetic field of 10 to the power of 12 Gauss. So, you now have a region which is permeated by vortices in the neutron component, which have a normal core and a 1 over r superfluid velocity field around the normal core, and you also have fluxoids in the proton fluid which is coexisting in the same region, which are permeated by a large number of fluxoids, where you have a normal core which carries the magnetic field with a screening supercurrent which flows around the fluxoid. So, that is the structure of the neutron star interior, where the rotation and magnetic field is carried. So, the magnetic fields in the neutron stars, you can see that you have the nature's strongest known fields occur in these objects, and the fields influence most physical processes in and around the star, and the fields can also evolve due to various transport processes, and the evolution depends on the internal structure and the field distribution, and the distribution itself depends on how the fields came to be in the first place. So, if the field permeates the whole star, then you will have these fluxoids going through the interior, which is carrying the field, and then the field permeates the crust, and you have the dipole field in the outside. If the field has actually not entered the superfluid core or superconducting core and flows only through the crust, then you have a set of currents which are confined to the crust, which which gives the source of the magnetic field. So, looking from the outside, these two field structures may look similar, but the long term evolution of these two will be very different. So, one hopes that with sustained observation of long term field evolution, one should be able to figure out whether the magnetic field in the interior is carried like this or carried like this. So, the evolution of the field is driven by different agents, the Lorentz forces of course, then ohmic diffusion, ambipolar diffusion. Ambipolar diffusion is important in the situation where you have a mixture of charged particles and neutral particles, which you do have in the neutron star. So, where the motion of charged particles with respect to the neutral particles, the charged particles feel the magnetic field, the neutral particles do not, and as the charged particles move in the influence of the magnetic field, they scatter off the neutral particles and thereby lose energy, which causes the magnetic field to evolve. So, that is ambipolar diffusion. Then you do have Hall effects, and you do have a heat flux, because the neutron star is hot in the interior and heat leaks out over time, or if the neutron star accretes matter on the top of the surface and the surface becomes hot and some heat may be going inside, and all of that can contribute to the evolution of the magnetic field. There are various mechanisms which people have proposed: a thermoelectric battery or inverse thermoelectric battery, reconfiguration of the field, the motion of the crust can also correspond to can contribute to the field evolution, as well as Joule heating. As the field decays, the energy goes into heat, and that Joule heating can feed back on the conductivity and hence also affect the further field evolution. The induction equation is one generalized expression which can be used to describe the evolution of the neutron star magnetic field. So, how does the combination of rotation, magnetic field and other properties of neutron stars contribute to a large number of observed exotic phenomena on these compact objects is a subject that we will deal with in the coming module.